Okay, now first of all, we need to know the name of this circuit. What's the name of this circuit? That's a full wave center tab. Rectifier circuit is the whole thing. So the first thing we're going to do is we can work this a couple of different ways. But remember, the biggest problem somebody has is remembering that we're only using 1/2 of the transformer, right? Remember that. First of all, we'll calculate the turns ratio. So we're putting 120 volts in. So we're going to call this V out, or V secondary, I guess you'd say. It would be equal to 120 divided by 10, so that's going to give us 12 volts. Everybody okay so far? Then we're going to look at the secondary voltage, and what I'm going to do is I'm going to say 12 divided by 2 is going to give me 6. Why are we doing that? Because we're only using 1/2 of the transformer. Everybody okay? Only 1/2 of the transformer at any one time. And that's the center tab. So V peak on the secondary would equal to 6 volts divided by 0.707. What does that give us? Okay, good. 8.4 volts peak. Then I'm going to calculate V peak out. V peak out is on the other side of the diodes, right? So it's going to be 8.4 minus 0.7. What does that give me? 7.7, right? Then I'm going to calculate my volts DC. My volts DC would be equal to 7.7 divided by pi 3.14 times 2, because it's a full wave rectifier. What does that give us? I'm listening. 4.9. 4.9. 4.9. And this is DC. So over here we're putting in AC, over here we're getting DC, right? Everybody okay? Okay. What's the next thing it asks for? Current in the load, right? So I of the load would be equal to 4.9 divided by 2.2K. Where'd y'all learn this at? DC, right? What would they give us? What's that? 2.25 or 2.3. Either one of both, okay. And this is milliamp. This is the milliamps, so that's K. Usually when you divide whole units by K, you usually get milliamps. Unless it's 100K, then you usually get microamps. Okay, so now we need to calculate the power in the load. So power in the load would be equal to V, which is 4.9 times 2.2 or 2.3 milliamps. And, normally we don't put units inside these equations because they don't cancel each other out. And this is milli, I'm sorry. That's what we got. And 1.2 milliwatts. Are we okay? Everybody okay so far? Then we calculate current in the primary. So I primary, we're just going to put PRI, would be equal to 11.2 milli divided by 120 volts. what would the current in the primary be? I'm listening. Picoamps? Yeah. Pico is to the 12th. That's microamps is low. So 93.93 microamps in the primary. Now, the way that the sheet is said is that's the fuse size, but that wouldn't be the fuse size. And while we're here, let's I don't think so. I think it's microamps. Huh? You can't take milliamps and divide it by 120 and come up with milliamps. Right? Understand? You can't take 9.3 milliamps and divide it by 120 and come up and get milliamps again. Because you'll lose 2 decimal points, right? And that's what we're saying. When you get the wrong answer, if you understand the math, most of the time you can tell. You can't tell if it's right, but you can tell if it's definitely wrong, right? So I know that I can't take milli, and not unless it's 1,000 milli, which would be an amp. Since I'm dealing with milliamps and I'm dividing by something over 100, we should expect microamp answers. And a lot of times that's what we do. A lot of times we can't tell it's right, but we know when it's wrong. So if I calculate D peak and I come up with a smaller value than RMS, then I know what? I know it's wrong. If I come up with a bigger answer, it don't mean it's right, but at least it's got a chance of being right. I changed the title on that because I think it gave Brian some problems. Anything that deals with the contents of the course is going to be in course content. So what I did is, where I said handouts, I changed it over to reference material. So everything that deals with the class, so chapter quizzes or topic quizzes are going to be in course content. Worksheets are going to be in course content, right? But inside the reference material, I put something in here that would help you. It's the National Electrical Code procedure for calculating transformers. And it tells you how to calculate what size transformer you need, but it gives you the quotes right out of the NEC for calculating overcurrent protection devices. So it says if I'm going to fuse the primary, and this is in section 405.4, it says if the transformer is, that's not what we're looking for. Nominal voltage, overcurrent devices. So what we're looking for is down here. It says such overcurrent devices rate. So if the transformer is rated at 600 volts or less, be protected with an overcurrent device, then what we need to do is 125 amps of the full load current. Input current, or the primary current, not the secondary current, the primary current, right? You understand that? And then it goes on, it says further, that also says if the primary current is less than 9 amps, then we're supposed to fuse it at no more than 167%. Now, it doesn't tell you can't go above it, below it, but it says you cannot go above it, right? You understand that? And then it says, goes on and says that the primary current is less than 2 amps, an overcurrent device rated set not more than 300% of the permitted current. So that means the smaller the current rating of the transformer, the bigger the fuse that you're allowed to put in there. So since ours is sitting out there at 932 microamps, yes. So 300% means you just multiply it by 3. And then usually we would round down to the next standard value. That makes sense? Yes or no? Because fuses come. So I would take, 93 microamps This would be one of those fuses. We had did I tell you about the fuse in one of our radio transmitters out at US Steel? If you checked it with an ohm meter, it would blow it because it was rated so low. This would be one of those. Most ohm meters, when you put it on the ohm scale, it puts out about 10 milliamps. So you would have to check this with voltage, right? Voltage applied. So what fuse would I use? So it'd be 930 or what? 903 microamps times 3. And then if it didn't fall on a standard value, what would we do? We would round down. Huh? I guess, I don't know. Sounds about right. Now if we fuse the secondary, and of course the best thing to do is to fuse both sides, right? So the primary, and this is why you need to understand power. So to calculate the primary current, then what you need to do is use power, right? Y'all understand? So I is equal to P over V, right? Everybody understand that? So I've got a 15 kVA transformer over here. We're going to calculate it in a second. So it says for secondary fuses, that's primary. For secondary fuses, if it's rated at more than 9 amps, then 125%. And if it's not on a standard rating, then you round it what? Up. If it's 9 amps or less, then the overcurrent device cannot be more than 167%. So what you do is you multiply it by 1.67, and if it didn't fall on a standard value, you would round the fuse down, right, to the next standard value. Are you okay on that? Which is pretty neat. You're not going to be required to do this, and this is up there, and this is a neat little handout. It tells you how to size the transformers, and that neat stuff. This is mostly built around 3-phase transformers. So we have a 15 kVA transformer over there. It's putting 208 on the input. So since it's 3-phase, by the way, we did talk about this, right? What we're doing with 3-phase is that we're transmitting power over 3 wires. So basically, you can over 3 wires, you get the power times the square root of 3. So this is what they're showing you to calculate that. So it's and by the way, transformers are not rated in watts; they're rated in volt amperes. So they're showing you how you do that. So this is a 75 kVA transformer. First of all, they took it from kVA and converted it to VA, right? Of course, you wouldn't have to do that because you know engineering on your calculator. Then they took the 750 kVA and they divided by 480 times the square root of 3. And what they're doing is they're compensating for the 3 conductors. So on 3-phase, if you measure the current and the voltage in 1 phase, then to calculate the VA, you would multiply it times the square root of 3 because the power is actually divided over what? 3 wires. Does that make sense? So they're still using the P over V, but it's 3-phase. You're going to take the voltage and multiply it by the square root of 3. So that would be 90.2 amps. And then of course 125% is 1.25. So this is what we would fuse it as. And we can't do it more than that. So since that isn't a standard fuse, then what would we do? We would round down to the next lower value. Does that make sense? So what they did is they chose 125 amp 3-pole circuit breaker. So this guy's doing breakers, but if you didn't, you would use 125 amp fuses in each leg, in each of the 3 legs. So the worksheet is kind of not quite always there when it says what fuse would you use. That is not the fuse. That's just what you would use to calculate the fuse, right? Does that make sense? Is there anything else we asked for? I think that's it. So are we okay on this one? Everybody okay? So let's see how that thing worked out. Anytime we do a ratio, what's a ratio? The ratio is out. The ratio for us is out over n. So what we're getting out is we're getting DC out, and then what are we putting in? We're putting volts RMS in, right? And then we can come up here and substitute that formula. So the volts DC for an alternation would be V peak times 0.637. And then VRMS is V peak times 0.707. So you notice what cancels? V peak cancels. So we can calculate the ratio of the input to output by using 0.637 divided by 0.707, and this comes up to be 0.9. And this is something that I just found out, which is pretty neat. So what's our RMS value in? So I'm going to say my volts DC is going to be equal to 12 times 0.9. What does it come up and give us? What's that? Oh, I'm sorry, wrong. Duh. What did I do? 6 times 0.9. So what? Okay, look. 5.4. 4.9. Okay, cool. Of course, why are we always going to get a bigger answer? Well, the bigger answer, this technique does not take in consideration the forward drop of the diode. It doesn't take it, but you get pretty dang close that way, can't you, right? So you could pretty much well check your answer. If I was taking a test, I would probably do it this way first, and then choose the closest answer. If they wasn't closest answer, then I might work it the long way. That's something we just got out of our book. I never had even thought about that before. But this is where the equation came. It's the output voltage divided by the input voltage. That's the ratio, and then we do two formulas, and it always comes up to be about 0.9. Pretty neat, ain't it? So we missed it. What we get out, 4.9, we only missed it by 500 millivolts using the other method. So using the other method, you're going to get extremely close. Are we okay? Now the next one is the half-wave rectifier. So this is a 5-to-1 transformer. So I'm gonna come up here and go V out. Well, this I shouldn't call it V out. V secondary would probably be more. We would equal to 120 divided by 5. What do we got? 24 volt. Then I would calculate V peak. We don't have to divide by 2 now, right? Because we're using the full transformer. So V peak secondary would be equal to 24 divided by 0.707. What does that give us? 33.9. V peak out, which is on the other side of the diode, would be 33.9 minus 7 tenths, which would be 33.2. My volts DC is going to be equal to 33.2 divided by 3.14. And we don't multiply it by 2 because it's halfway, right? So what does that give us? We okay?
I hear you going step by step with which I think I need a visual to see exactly what you mean that you cross it over to the other side of the diagram. Like, I need to see
I don't know what you mean by I don't. This is what do you mean by visual?
Well,
so right here,
it usually be that
this is VP secondary.
Okay.
This right here is VP out. So what we lose is we lose that 7/10 of a volt across the diode. So that's why we subtract 7/10 right there. Is that what you want to show? Now, of course, when we're talking about VP out, so this is what we're getting out of this one. If we looked at this with an oscilloscope, this is actually what we're getting. And this is what we see on a half wave. Right? And this guy right here, the average DC value of this guy right here is VP times 2 divided by 5. Or we say 2 VP over 5. But that's averaged with this right here. So this is an average of what? 0. So basically, if I average by 0, what's it going to do? It's going to drop that 2. So that means on a half wave, the DC average is V peak over pi. On a full wave, it's 2 V peak over pi. And goes a full wave, we get this right here, right, Charles? And then this would be 2 V peak over pi. And this would be 2 V peak over pi. This would be 2 V peak over pi. No matter how you add them, you divide them by 4, then you're going to get 2 V peak over pi, 0.637. Everybody understand that? That makes sense now? Okay. So what's the next thing we need? Next thing we need is the power for the load, which is so I of the load, I think we asked for that, would be equal to 10.5 divided by 1K, which is going to be 10.5 milliamps, right? That's one thing nice about 1K, it's 1 milliamp per volt. The power of the load is going to be equal to 10.5 times 10.5 milli. What are we going to get? 100 what? 125. We're not going to get a 25 there. 125 milliwatt? Huh? Well, somewhere it didn't get rounded. Does it say 10.5 volts? Well, see, I can see 5 times 5 is what? 25. So I don't know where the 100. I'm trying to see where what's that? Okay. So so when we round, we're going to round to 1 decimal point. So when we round, it doesn't mean drop in digits, right? That's one of the biggest problems we have in electronics. For some reason, people think when you round, you just drop decimal.
I got 110.
It's 4.9 or 5.9?
It's 110.
Yeah, so what this should have been rounded to is what? Yeah, it should have been around 10.6, right? And what's the rule for rounding? So we got 10.59. What's the rule for rounding? Well, what we're going to do is we're going to look at this digit. If it's got more digits, we'll work from there. But what's the rule for rounding? No, 5 and up. Yeah, if it's 5 and up, you go up. You take this digit up. If it's 4 or 4 to 0, you go. If it's 0, you stay where you're at. You round down. Okay, so actually this should have been 10.6. What do I have in my worksheet? 5.9 here. And you can see this gets a lot closer.
Got 110.
So I need to go back and correct that on the worksheet. But it's okay, it's still close enough. What's the current in the primary? So the current in primary, let me read that. So the I in the primary would be equal to 110 or whatever that is down there, milli, divided by 120 volts. Or 120, what does that give us? Huh? No, we can't be 933 milliamps. I can't.
916 micro.
Okay, and let's look at this and try to figure out what's going on here. That's the problem. For one thing, my bottom number is whole, my top number is milli. So right off the bat, I know I cannot get a number bigger than what I start with, right? So when your divisor is bigger than your dividend, then you got to come up with a smaller answer. So I know it gets kind of confusing every once in a while, but what you got to understand is when it's got to be wrong, right? So even if this was 110 and this was 120, we would still come up with a number smaller than 110. But this is 110 milli divided by 120. So odds are our answer is going to be in micro, right? Yeah. Microamps. So we deal with very small currents here, of course. But think about that. That transfer over there is a 15 kVA transformer, and it's a step-up transformer. So my primary current, I in the primary, would be equal to 15,000 kVA divided by 208. So what's the current in my primary? If we were running the transformer fully loaded. And this is what you would do to size the fuse. So when you size the fuse, you size it for the rated current of the transformer, not the load current, the rated current of the transformer. So what would be the rated current of the transformer? Times the square root of 3. And why? Because that's a 3-phase. So you probably have to put this in parentheses, guys. Now, if you work with 3-phase all the time, we use 1.73. So it'd be 15,000 divided by 208 times 1.73. So there's a lot of things you learn when you deal with electricity. Like you learn the square root of 2, which is 1.414. You learn the reciprocal of the square root of 2, which is 0.707. What's that? No, it can't be kilo. Really? Okay, that's what I thought. Don't y'all gonna have to be careful. This is a common mistake. People will say 1500 divided by 208 times the square root of 3. It's not that. It's 1500 divided by it's this. You got to put it in. You got to put it in. So this is what most people would do. They would say in their calculator they'd say 15,000, and then they'd say divided by 208, and then they had equals, and they'd say times 1.73. That's not the equation. Y'all understand that? So I'm gonna go ahead and say 208 times the square root of 3, 1.73, which is, so I'm gonna say 15,000 divided by 360. That's 360. And that's a common mistake. People don't get it right in their calculator. This is why your calculator has parentheses, right? You understand that? So if you say 1500 divided by 208 times 1.73, it's going to multiply your answer. And what's that? 41 ounce? And that's a common mistake. People just punch it in their calculator and they don't use those parentheses. The secondary current, this is a step-up transformer, so it's a 408 transformer. So my secondary current would be equal to 15,000 divided by twice that, which would be 416, right? Times square root of 3. So it's a 1 to 2 transformer. So that's going to be 15,000 divided by open parentheses 416 times 1.73 close parentheses equal to 20.8 amps, about 21 amps. And what a lot of people don't understand is power in. So we don't have any, y'all understand this. Number one, energy in is, energy out is always going to be less than energy in, right? You understand that? Here we're assuming the transformer doesn't lose any energy, but that's not true, but it's very, very small. So 41 amps, what would I fuse this thing to? Well, I would come up here, multiply this by 1.25. Then if it fell right on the fuse, that's the one I would use. If it wasn't on the fuse, I would round down, right? So what doesn't a transformer change? Power in, we assume power out equals power in. So what it varies is its current and its voltage to produce that power, right? Okay, so I guess that's it for that circuit. Are we okay? Then the last circuit is a full wave bridge. Oh, we didn't use the shorthand method. So the shorthand method would be, let me go ahead and, I'm going to go ahead and copy this over and we'll, I can get bridge. So the shorthand method for the other circuit would be equal to what's our secondary voltage? What's the RMS voltage on secondary? 24 volts. Yeah. Yeah, on the last one, not this one. We're going to see how close it comes up to that. So it's going to be 24 times 0.9 times 0.9 reds. Divided by 2. Now here you can do that because that's on the top. But just hit equals. So make sure that you get on your calculator, do this first. 24 times 0.9 divided by 2. Why are we dividing by 2? Halfway. So what does that come up and give us? 10.8. And what did we get when we went to longhand? Huh? That's really close. Ain't that neat? Now, I'll put that formula in the formula sheet, guys, if I got room. But that's in the textbook, by the way. I didn't even know that. So even though I've been teaching this so long, I still learn things.
0.9.
Huh?
0.9. 0.9.
I showed y'all how it came up. How did they come up with this? So first of all, they said, okay, the way the factor of the thing, or what we call the transfer function, or whatever you want to call it, would be the output. So what we get out is we calculate that by V peak times 2 V peak over pi, which would be 0.637. Now that's our output. Our input is volts RMS, right? Volts RMS, we calculate volts RMS by taking V peak times 0.707. So what do we do? What cancels? Okay. So that means the factor between my input and my output is going to be 0.637 divided by 0.707. What's 0.637 divided by 0.707? Huh? 0.90001 or something like that. So this is the way we calculate the output of a full wave bridge. This is the way we calculate V peak. So this is what we've been doing. We've been calculating V peak, then we've been calculating we've been calculating V peak from RMS, and then we've been taking that and calculating the output. Well, what we did with this equation is went ahead and came up with a fraction that takes care of those first two things. The only thing it doesn't consider is the what? The diode drop, the drop of the diode. So what we're saying is that this is going to be very accurate on a power supply circuit. And they call this the approximation method. So we know we're getting approximately 90% of the input turns up to be DC. Of the RMS voltage, not the peak voltage, of the RMS voltage. And they don't show you how they solve it. All they did is they threw out 9%. They threw out 9%. They threw out 90%. That's all they threw out. But when I started thinking about it, all these calculations we go through. So what's the first thing we do? The first thing we do is take V peak and do what? Calculate. We take VRMS. We take V peak and calculate VRMS. And then what do? Then we take VRMS and calculate the output voltage using 2V peak over pi. But 2V peak over pi, so here's V peak, would be equal to 2. So we could split that out. So the DC average of an alternation would be equal to V peak times 2 over pi. Well, if you take 2 over pi, you come up and get 0.637. So what we're doing is we're combining a lot of what? A lot of math. But what I'm saying, guys, You know, most of the time that 0.9 is good enough for government work. And why is that? It's close, but when I got a 120 volt transformer, that's what the transformer's rated at. This transformer right here, wherever's that? Where's that power supply? The transformer I have is rated at 110 volts. This transformer is rated at 120 volts. Which one's right? Both. Because there's really no guarantee what voltage you're going to get at your house. NEC says, National Electrical Code says 120 volts plus or minus 10%. So you can get 90%, you can go 10% down or 10% up. That's what they say. So NEC uses 120 volts all the time. So what we're doing is we're using, and then if I rate my transformer at 120 volts, what's the odds of me getting 120 volts? What are we getting right here? We've measured it several times. What voltage we have here? About 112, 113 volts, which is not 110 and it's not 120. But when I do my calculations, we're making approximations. Okay, so let's do this one. We'll do the longhand method and then we'll do the shortcut method. See what we come up with. So first of all, I'm going to calculate B secondary. I'm going to take 120 and I'm going to divide that by 12. So that gives me 10 volts, right? This is AC. Then I'm going to come up and I'm going to calculate DT secondary. This is going to be equal to 10 volts divided by 0.707. What does that give us? Then I'm going to calculate what we refer to as D peak out. This is on the other side of the diodes. This is going to be 14.1 minus 1.4 volts. Why 1.4? Why 1.4 here? Now it's going through two diodes, right? 0.7 of a volt per diode. What does that give us? Can you do 12.7? Then I would calculate my my DC. It's going to be equal to 12.7 over pi divided by times 2. Now you could take the 12.7 and you could multiply it by 0.67, and what that's doing, 0.37, excuse me. What that's doing is go ahead and doing this, right? You understand that? So what do you get here? $8.1. What do you get up here? Should give you the same thing. Very, very, very close. Yeah. I just like, you can use the 0.637 if you want to. Y'all understand that? Y'all can use 0.637 if you want to, but I like 2 peak over pi because to me it's so easy to remember. Now I know the 0.637 now because why? I've used it so long. Okay, so we calculated our output voltage. Now I need to calculate my load current. I, the load, would be equal to 8.1 divided by 8.1, Rich, divided by 3.3K. What's it give me? 2.4 milliamps. 2.4. Where did I get 10 from? I think I even said 2 when I 2.4 milliamp. Then we calculate the power in our load, which is very important. Did y'all do that on DC, on every resistor, every circuit that you have? Because this is what we're paying for, right, is power, and plus this is the way we size our resistors. So this is going to be equal to 8.1 times 2.4 milli. Well, this is going to be a little bitty. What we got? What's that? And then the I in the primary would be 119.9 milli divided by 120. So we're going to get microamps again, right? $165 microamps. So the shorthand method says I could take my DC out. I could take my voltage right here, 14.1, and multiply it by 0.9. Let's see how close we could probably get real close. What does that give us? What's that? Yeah, we're doing this. Let's do it the other way. Go ahead. Just give us what? Brandy, what does it give? 10? That gives us 12.6. How did I get what?
19.9 at 8.1 times 2.4 milli.
Yeah, I didn't do it. It's going to be over 16, so it looks like it's going to be okay, right? Is that right?
I had 19.4.
Huh? Yeah, 19.4. So our secondary voltage is 14.1 times 0.9 equals 12.69. So that we messed that a lot. Oh, I'm sorry. You're right. The RMS. Yeah. I just saw the wrong number. So it's 10 times 0.9, which is 9. And then 12.7 times 0.9. Oh yeah, that won't work. So if we do the shorthand method, we come up here and say this come up to be what? 9. Oh, and I'm doing it wrong. Y'all excuse me. I'm seeing different numbers. So this is VRMS. So volts DC is VRMS on the secondary would be 10 times 0.9, which would be 9 volts. Now here our error is a little more. Why is our error a little more? Because here we have two diodes that we don't see, right? So that's the worksheet, guys.
I understand it'll be more than.
I hope so. There's 3 of these on their test next week. There's another worksheet up there that you can do. It's up to you. I'll make it available. So what I'm going to do on this one is I'll go ahead and let me go to, okay, so course content. And what I'll do for the next worksheet is, so we're dealing with semiconductor diodes, right? And then here's the worksheet right here. And the 2 worksheets that we went to so far is worksheet 1, that's the one we went over. Now I gave you a copy of the key, but I'll make it available in case you lose that one. And then what I'm going to do is I'm going to go ahead and make the second worksheet available. And I'm going to go ahead and make the key available. And what that means is the test, where do y'all think I get the questions, the circuits on the test? From the worksheet. So that means the circuits on these worksheets are going to be on the test. Not all of them, just one. Y'all understand that? Yes or no? So it would probably kind of be smart for you to go ahead and do what? Number 2, and then once you do it, check your own answer. Okay? You see we got several worksheets inside this section. Also, what you need to make sure you do before we take our test is you need to come in and take these topic quizzes. These count towards your grade. And right now we're only on part 1, which should be the rectifier circuits. Let me make sure. Yeah, so this has probably got some semiconductor stuff in here. No, these are not rectifier circuits. So the other one, so this is one you need to do. And then the second one that we need to look at is, sorry guys. And if you look at the course syllabus, it says these topic quizzes are supposed to be done within 7 days after we complete the lecture. Has anybody does a topic quiz on AC? No, that's in the syllabus. So topic quizzes are due within 7 days after we finish the lecture on a topic. And this is something you're going to have to keep up with, right? You understand? How many's done the topic quiz on AC? Huh? You started it? Then the other one that we've got through with is safety and symbols, right? And so we're working on this one right here. And I think we just finished the second part of this. Let's see what's in the second quiz. I think these are full wave rectifiers. So yeah, this is what we're finishing up tonight. There's the basic makeup of a power supply, which we've gone over several times, right? Full wave, half wave. So what we're fixing to do is fixing to go to lab. Then next Tuesday, we'll talk about troubleshooting these power supplies. Make sure there's no and we'll talk about filtering. Are we okay? Probably not. I just realized y'all had a bunch of work today, right? That y'all should have been doing all along. And I think test is next. When? Not, yeah. So it's 2 weeks from this. We got another week. So we'll get through filters. We're going to stick filters on here, and it'll be a little while before we get to regulators. Then we'll come back. Once we get to do regulators, we're going to come back into chapter, I think it's chapter 5, and talk about Zener diodes. It's just they kind of got it out of sequence. They threw the Zeners in there before we understood what do we regulate, right? You understand that? So regulators. So we teach it right down the block model. We teach basically the transformers first, a little bit of transformers, not a lot. Then we teach the rectifiers. Now next we'll teach the filters, and then we'll come back and do the rectifiers. So I think it's better to teach the power supply from the front all the way to the end. So that's what we do. So y'all got any questions on that? Okay, so y'all got what lab are y'all working on? Y'all working on the diode characteristic lab, right? And then after the diode characteristics lab, you'll work on the rectifier. We'll start on the rectifier circuit. Okay, so we got 2 good labs to do. When y'all get along a little bit, what we'll do is we'll come into the lab. We'll come into here and we'll do that reverse breakover as a group. We already talked about that, right? So because we're going to have over 100 volts to break that thing over, and y'all don't need to be dealing with that much DC right now. Okay? All right, guys, let's go to lab.